Swayam Prabha. Digital India. Educated India. So, remember we said that to trim the aircraft at different speeds, you need to use elevator, right. So, trimming is besides forces that you have to balance, the moment also has to be balanced, right. And right. So, delta E trim is right. Okay. So, let us try to look at how much elevator you will need for change in angle of attack, right, per unit deflection or per unit change in angle of attack, and this is right. Okay. You can write this expression also as so clearly you see here that to get a change in CL trim you need to deflect elevator, and that is going to depend upon this quantity, isn't it. And what is dCm over dCl? It is the measure of pitch stability, right, static margin, isn't it. So, clearly the amount of static margin that you have, or the pitch stability that you have, is also going to determine how much force a pilot is going to feel, right, when he is trying to change the elevator, right. Pilot is the one who is going to pull the stick or push it, right, and that force he has to apply depending on this, right. In other words, depending on the stability that aircraft has, is going to decide how much force a pilot is going to feel, right. Okay. So, so pilot will feel the stability through this equation 1, right. So, let us try to look at the mechanism by which you will change the elevator deflection, and this is roughly how it should look like. Fs is the stick force and this is a pull, right. So, pilot is sitting somewhere here and he is pulling the stick towards himself. Okay, so maybe this line can be shifted here. And this is the arm that he has, right. So, this is going to so delta E up is negative, right, that we have said yesterday, and so there is a hinge about which this elevator is moving. Okay. So, you apply this force, pull it towards yourself and you will see a elevator deflection which is upward and that is negative, right. If I want to find out what this force should be, right, I have to talk about the moment that it has to overcome, isn't it. Elevator is in the flow field. So, there are forces acting on the elevator. Now, you want to overcome that force when you are trying to change the elevator deflection, right. So, this is your elevator hinged at this point, right, to the horizontal tail. So, let us say this is the some chord length, okay, which is measured from the hinge line, okay, and this C is the chord length of this tail or any surface, actually any control surface, right, because similar thing we will have to also repeat for rudder or aileron, right, whatever we are talking about here, similar things, similar explanation we can give also for other control surfaces, right. So, hinge moment is the moment about this hinge line, okay, that the pilot has to overcome when he is applying the stick force. Okay. So, the expression for this hinge moment right, it will be all along the tail. So, that is why I am writing this hinge line and this is equal to this, okay. CHE is okay. Let me draw this picture which will make things clear. So, this is your elevator, right, and hinge line is this. Okay. Okay. So, let us try to balance out the work, okay, work that this force, stick force applied by the pilot. Yeah, tail, it will be slightly changed, right. So, actually again I am going back to what I said, these are some estimates, okay, and no analytical expression actually can be correct. You have to put everything in the internal and measure the moment and forces, okay, if you want to get an exact answer to any of these quantities. Okay. So, this pull is a positive force, okay, when the pilot is trying to pull the stick towards himself, that is a positive stick force, and that gives me delta E upward, which is negative. And let us try to find out this force. This force, no, if the pilot is not applying, someone else or some other mechanism has to to do this job, right. For example, if you want your aircraft with control systems mounted, then this force will not be directly applied by the pilot, but automatic control system can do this, isn't it. So, you press something and that at the press of a button this should happen, elevator should deflect, right. So, actually they will not even have to do this for bigger aircraft where you have strong control systems in place. You only define the flying condition, okay, and then everything will be taken care of. Okay. So, what is the work done by this force in deflecting this stick by this angle? F into right Fs into Ls delta S, right. Delta S is a small angle and that has to be equal to the work that has to be done, right, by this, which is H E into delta E, right. So, what is Fs? Fs is H E into delta E over Ls delta S, right. This is called, this quantity in the bracket is called gearing ratio. All right. So, let us try to analyze one situation where elevator is free, okay, it is not changing, and the pilot wants to just leave the stick, then what will happen? Okay. So, remember that what I am saying is that when you are designing a control surface, you have to remember three things. Okay. Now, will depend upon three factors. First is control effectiveness, right, and there is also the control power that related to the control power, right. So, if you remember, we wrote this expression for Cm delta E, which is change in pitching moment that you can get by changing the elevator deflection, and that the expression for that was this, right. So, Vh and this tau is a function of the area of the planform of this flap and the area of planform of this tail, right. So, this parameter was a function of this ratio of the areas. Okay. Vh is what? Vh is right. So, you have some parameters which you can adjust, but you remember you also when we are talking about stability, there also we said that we can use these parameters to change the stability characteristic, right. So, now stability characteristic while changing, you are also actually changing this control power, right, if you are doing it through this quantity tail volume ratio. Okay. Second factor is hinge moment. Hinge moment is nothing but the aerodynamic moment that a pilot has to right. Now, the third factor is, can we reduce this moment, okay, by doing something, can we reduce the hinge moment somehow. I think I don't know. So, how you can change the hinge moment? No, the moment that a pilot has to overcome, no, that is a third factor that one has to remember while designing the control surface. Okay. So, let us look at a case when the pilot has left the elevator to rotate freely, okay, is not applying any force. What will happen in such a case? What will happen to the hinge moment? If a surface is, if something is allowed to rotate freely, what should happen to the hinge moment? 0, right. So, let us look at what happens in such a case when elevator is not fixed, but is free to rotate, right. You are not holding the elevator somehow. No. So, let us look at now. So far we have looked at stick fixed stability, right. Now talking about one case, and that stick fixed was this, okay. So, you have fixed the elevator, elevator is not allowed to move from that fixed position, right. Here is one case where elevator is left free, no, that there can be situation like that. So, if pilot leaves the stick, he does not do anything, what will happen to the stability of the aircraft? That is what we are going to see through this. Okay. So, this hinge moment coefficient is going to depend on hinge moment is the aerodynamic moment that is coming over to this small flap, right, that has to be overcome, right. What is it going to depend upon? Angle of deflection, angle of attack, right. So, CH alpha t angle of attack at the tail, right. So, also going to depend upon the elevator deflection, right. If you have a tab, which we will talk about later, okay. If you have a tab which is a surface attached to the elevator, we will talk about this little later. It is also going to be a function of the tab deflection, okay. Plus there can be a residual moment which is there forever. So, you have to overcome that, and this CH naught, right. Now, what I am saying is elevator is free to rotate, okay, and let us try to make things simpler. Let us drop this for now, and CH naught is also 0, okay, assume that. So, we have right. So, delta E free. So, now you are on the ground and you are not applying any force, and let us say there is a flow, what position that elevator is going to take, that is what we are trying to find out from here, right. Right. So, this is the free position of the elevator, and these quantities are actually positive, okay, both of them are positive. So, for alpha t which is positive, delta E is going to be upward, right. So, free elevator deflection and they are positive, okay. So, there people have done some measurements and they have found that these two parameters are positive, okay. So, automatically elevator should show an upward deflection, okay, without doing anything whenever there is a flow over the airfoil. Let us look at what happens to the lift coefficient of the tail in such a situation. So, CL alpha t is going to be right. So, automatically you see this component, right, and that is no, this CLT delta E is this, okay. Into and call this some f, okay. So, this total quantity becomes CG of the moment is about CG of the aircraft, yeah. It will be small and uh, okay, I will come back to your question later, okay, because yes, aerodynamic forces are large, but we'll see if it falls into this third factor, okay. We have written there aerodynamic load and mass balancing. Yes. Can I come back to this later? Maybe I'll also have to think a bit on this. Okay, so this CL alpha that we see is modified, right. So, if you look at CL alpha, the new CL alpha, because of the free rotation of the elevator is right. Now let us go back and see what happens to our Cm naught and Cm alpha. So you see how many derivatives one has to worry about when you are designing a accident proof aircraft. Now you can design your MAV, small MAV, and let it have n number of accidents you do not care about, but when people are designing a full passenger aircraft, 400 people or 1000 people sitting inside, then you have to worry about each one of these terms. So Cm naught new is Cm alpha is also going to change, right, because the lift curve slope of the tail is changing, right, for free elevator deflection. So clearly something has changed, right, Cm alpha has changed, right, and that is going to depend upon this new slope of the lift curve for the tail, right. Okay. So I am going to see a change in what? There is something which is changing now, right. What is that? Cm alpha is changing, so static margin is changing, right, stability margin is changing, right, and that automatically implies that the neutral point location is changing, right. Which way? It will depend upon what this f is, right. If f is positive, then x and p prime is going to be will reduce. If f is negative, this right, so it will be going back, right. So if I say this is my x and p, the new x and p is going to be depending upon what this f is, okay. If f is less than f is positive, then this 1 minus f is positive and lesser than 1, right. Then you are going to see a reduced stability margin, right. Okay. So now I will write down the difference of the two. You have to remember that all the measurements are from the wing leading edge, right.
Subtracting CM alpha from CM dash alpha, that one will get, the one will go away. You don't have that 1 minus
You don't have 1 minus f?
f. The one will go off when we subtract.
Then I have to put a prime here.
So that if we expand CL alpha t dash, it will be CL alpha t minus f into CL alpha t. The CL alpha t will get cancelled when we subtract.
Okay, don't have to go that far. You set this to 0. Then this xcg is x and p prime, right. In the other case,
When we are subtracting, the one will go.
okay, let's try to do that. So I think you are right.
1 by CL alpha.
Yeah. So x and p prime.
CL alpha w is the one. So CL alpha t minus
CL alpha t minus. Okay.
just be minus f.
It will be
Minus f into VH theta. CL alpha t by CL alpha w.
okay. So stick fixed, stick free, static margin is okay. So I go back to the old question that I asked, right? How far ahead the CG can be, right? This question I asked some time back, and did we also find an answer to that?
Then we said it will be till the neutral point.
No, neutral point is the most aft. Most aft. Now it's going to depend upon this also. If the elevator is free, then x and p prime is the most aft limit of the CG, right? I want to find out the most forward location of CG. Conventional situation, okay, wing camber is positive, and now we are looking at how far we can move the CG in the forward direction, not in the backward, right. So, aft is moving towards the tail, okay, forward is moving towards the leading edge, right, or the nose of the airplane. Now, I want to find out that will give you the maximum stability, right. CG most forward will give you the maximum stability margin. Okay. So, any answer to that? See what is happening. No, positive wing camber, we are trying to create a negative moment through the wing. Now I have to adjust that moment through tail. So I start changing the elevator up, right, so that you have force down on the elevator or the horizontal tail, and it's going to balance that moment which is coming because of the wing, right. So CG definitely is now ahead of the wing, isn't it? That's the only way I can maintain CM CG equal to 0, right. How far ahead?
We should balance the moment from the wing to the moment from the tail.
That is for maintaining the trim, maintaining the trim, right. CM equal to CM CG equal to 0. So CG CG is now here, right. Now, so definitely I have to produce a lift at the tail which is downward, and this is going to create a moment about CG like this, and this opposite. What will it depend upon? It will depend upon the maximum elevator deflection, right, maximum positive elevator or elevator up deflection, which is no, elevator you cannot just keep on increasing, right. After some point there will be stall, separation of flow, and the lift will start decreasing, right. So that is the delta E max that you can get positive or an added lift or advantage of lift, right. Once you start going beyond that delta E max, there will be stall and separation of flow, and this LT will start decreasing, right. So that delta E max up to which you keep on seeing this LT down increasing, right. Right. So
in this configuration, the wing has to produce an additional lift, right?
wing has to produce additional lift.
Because there is a component of lift downward by the tail, we have to balance the weight.
Yeah, you have to balance the weight.
We have a stability versus wing
Yeah.
load.
Okay, so let's try to write an expression for that. Okay. So, remember we already found this del T delta E over dCl, and that was minus of Cm alpha, right, over and from this you can find out this is going to depend upon the static margin, right. Cm alpha is going to give you the static margin. Okay, so I am now writing down the F is for the forward, okay, forward CG location is CL max will be corresponding to the maximum LT that you can get, okay, corresponding to this delta E max, right. So, any question? Okay, we can stop now.